Hi everybody, welcome back. In this video we are going to start talking about Jupiter's moons, in particular Io, after we give a brief background of the moons. So currently Jupiter has at least 79 known moons whose orbits are presently known. The largest of these is Ganymede. In fact, Ganymede is the largest moon in the solar system. It's larger than the planet Mercury. Callisto is Jupiter's second largest moon. It's just a little bit smaller than Mercury. And the four largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean Satellites because they were discovered by Galileo back in 1609. Now, Jupiter's other 75 known moons are actually very, very small. Together, they make up much less than 1% of the total mass of Jupiter's moons. So that's kind of in stark contrast to the Saturn system, which we'll discuss in the future, which has something like a dozen medium-sized moons after one really big moon, and then a bunch of smaller ones. So, in any case, most of Jupiter's small moons actually orbit in retrograde orbits, which is what you would expect for objects that are captured asteroids, which is what most of Jupiter's moons are. So, as I mentioned, they were discovered, at least the first of them were discovered in 1609 by Galileo, and there weren't any more that were discovered until the 1890s, and then after that, a bunch more have been discovered with telescopes, photographic plates, CCD images, etc. And they may have been independently discovered by a guy named Simon Marius. And in fact, the names that the Galilean moons were given, Io, Europa, Ganymede, and Callisto, after Jupiter's lovers in Roman mythology, were actually assigned by Marius. So, this discovery proved that Earth is not the only object in the solar system that can have other things orbiting around it. One of the big points that people had in favor of or at least that people used to justify the Ptolemaic geocentric model, was that if Earth was moving, it might leave the moon behind. Well, clearly Jupiter was moving no matter which system you believed, and it wasn't leaving its moons behind. Okay, all four of the Galilean moons are bright enough to be seen with the unaided eye, except it's just that Jupiter's brightness is, well, so grand that it overwhelms them and we're not actually generally able to see them. Ganymede and Callisto are far larger than our own moon. In fact, as I mentioned already, Ganymede is larger than Mercury. Io is slightly larger than our moon, and Europa is a little bit smaller, but it would appear far brighter if you replaced our moon with Europa, because Europa is a much more reflective body. And, interestingly, the density decreases from innermost to outermost. As we're going to discuss soon, there's a very good reason for that. So, here's Galileo on the left and Simon Marius on the right. Now, Simon Marius's official, quote, discovery statement of the moons puts them in spots that were exactly where Galileo had them in his discovery, which was quite well known. So, at least in terms of his announced discovery, Marius may have copied from Galileo. Here are relatively modern views of these moons taken by the Galileo Spacecraft. There was a spacecraft that was sent to Jupiter that arrived there in 1995 that was named after Galileo. It studied Jupiter in detail, as well as Jupiter's four big moons. And notice that they have very different looking surfaces. In fact, going from left to right, Io, Europa, Ganymede, and Callisto, going from innermost to outermost. You'll notice that Io has no impact craters. Europa has very few impact craters. Ganymede has more, and Callisto has a whole lot more. So this increasing number of impact craters is indicative of older and older surfaces. Io is a surface that's constantly being refreshed, and Europa is to some extent as well. These are kind of older cutaway models of the interiors of these moons. We now have updated versions of these, but I still show this slide because it shows all of the moons together, and you can see some noticeable contrasts there. Notice that Callisto does not even appear to be fully differentiated. It might not have a noticeable core. Now, why do Jupiter's moons decrease in density going from innermost to outermost? So it all goes back to the fact that at least the Galilean moons decrease in density like that. It all goes back to the fact that they formed along with Jupiter out of the presolar nebula. So the Sun formed, Jupiter formed, and then Jupiter's moons formed, or at least the 4 big moons formed. And the idea is that closer to Jupiter, it is hotter because Jupiter is radiating a lot of energy as it is forming. And so the closer you are, the hotter it is, which means the closer you are to Jupiter, the more volatile compounds like water are going to be evaporated. So Io lost all of it, whereas Callisto has quite a lot. In fact, Callisto is also, it's kind of a mix of ice and rock and rubble, so to speak. Now, another result of the fact that they were close to Jupiter and that Io is the closest is that basically Jupiter is kind of like a mini solar system. It's like another model, including things like the frost line, so to speak, of the solar system with the planets around the sun. So without further ado, let's talk about Io, the innermost of the Galilean moons. Io is not the innermost Jupiter moon. Metis, Adrastea, Amalthea, and Thebe, those inner moons that have something to do with Jupiter's rings that we discussed in the last video, those are Jupiter's innermost moons, but they are far smaller. Among the Galilean moons, the ones that really can be seen in the Jupiter system by even just binoculars quite easily, Io is the innermost of those, and it's also the densest. Now, this is a true color image of Io, taken by, I think this one might be taken by the Cassini spacecraft, but you can see first lots and lots of yellow, and also a number of other colors. See some reds, some whites, greens, very dark greens as well. A little bit of trivia that you don't really need to know about Io. So Io is a little bit bigger in radius than our own moon. It's also denser than our moon, so it's a bit more massive as well. Our moon has a density of like 3.3 grams per cubic centimeter. And it's also the most volcanically active body in the solar system. Quite a bit more on that very soon, but that's one of the big points to keep in mind with Io. It is the most volcanically active body in the solar system. In fact, it has over 400 active volcanoes. Just another look at one of the hemispheres with a recently erupted volcano right here. Notice that after a recent eruption, you're going to get, in the case of some of the volcanoes, depending what kinds of compounds are present, this nice red plume, whose color will eventually change. So the volcano Pele is about the size of Arizona. That's really what we're dealing with right here. And it has this large red ring of this spewed matter. And there's another large volcano, Loki, I believe that's this one right here, which has that, it's larger than the big island of Hawaii, but the whole thing is essentially an active volcanic caldera. This thing actually emits more heat than all of the volcanoes on Earth combined. So in fact, it emits something like half of Io's thermal energy. Here's a very, very basic view of Io's interior, where you have a crust, and inside of that you have kind of like a magma ocean, so to speak. In truth, it's probably a bit thinner than that, and there's more structure than that, so again, this is just a very basic picture. We don't know for sure exactly what it's like on the interior of Io. These are 4 potential modern pictures, modern being like as of about the year 2020, different ideas of what the interior might be like on Io. The one in the upper right is the one depicting a situation of a global magma ocean. You have that to some extent with the upper left and lower left as well. Whereas with the lower right, you're dealing with more of a situation of just kind of bubbles of magma. The core of Io, primarily iron. The mantle is mainly molten silicate, and you also have a silicate crust, so we're talking about compounds of the element silicon. And the mantle also contains a lot of sulfur, and the sulfur is what gives that yellow color once this erupts to the surface. In fact, you'll have some very spectacular eruptions, as well as just continuous kind of spewing geysers with some of these volcanoes. Now, since Io formed so close to Jupiter, all of its water evaporated. In fact, the lighter elements and lighter compounds evaporated as well because of the heat of the proximity to Jupiter during the formation of Jupiter and the Galilean satellites. So as a result, Io is the most dense. Now, why is Io so volcanically active? I mean, it clearly can't be the decay of radioactive elements, because after all, Io is of similar mass and size to our moon, and our moon hasn't been geologically active for a very, very long time. But Io is the most geologically active body in the solar system that we know of. So this comes down to tidal forces. So we need to recall a few things about this. First, recall that the strength of tidal forces is inversely proportional to the cube of the distance from a massive body. So that's one thing to keep in mind. Io is the innermost of the Galilean satellites, so it experiences the greatest tidal forces from Jupiter. Now I do want to go back to the trivia page about Io. Notice that the orbital eccentricity, let's see, do we have the orbital eccentricity? There we go. It looks like a very circular orbit, 0.004. In fact, to two significant figures, it's 0.004. So it seems like a very, very circular orbit. But the thing is, Io is so close to Jupiter that even that slight non-circularity in the orbit can make a big difference in the amount of tidal forces that Io is going to feel. When it's at its closest point, it feels stronger tidal forces than when it's at its farthest point. So as a result, that means that as it goes around, it gets stretched and compressed. Well, why does it have a non-circular orbit to begin with? I mean, it's actually close enough to Jupiter that it's tidally locked. Well, here's the thing. There is a resonance with two of Jupiter's other moons, Europa and Ganymede. So Europa is tugging on Io at the same point every time in Io's orbit, and so is Ganymede. So Io orbits 4 times for every one complete orbit of Ganymede. Io orbits twice for every one complete orbit of Europa. So these tugs from these other moons are what make Io's orbit slightly elliptical. As a result of this slight ellipticity in the orbit, that means that Io experiences these changing tidal forces. So you often hear people talk about the power of Io being this, quote, gravitational tug of war with Jupiter's other moons. The whole point of this tug of war isn't that the tug of war powers the volcanoes or anything like that or gives it energy. The point is that it takes Io into a slightly elliptical orbit, and because of that slightly elliptical orbit, you're dealing with changing tidal forces. And changing tidal forces cause different amounts of stress and strain. If Io had a perfectly circular orbit, yeah, it would have strong tidal forces, but they would always be the same tidal forces, so Io would always have the same shape. But because of the changing tidal forces, Io's shape is constantly changing a little bit. And this change in shape due to these changing tidal forces provides about 90% of Io's internal power. Now, there's another power source caused by something called Motional Emf, the fact that Io does have quite a noticeable iron core. And as it revolves around Jupiter, it's going through Jupiter's magnetic field. And whenever you have a conductor that moves through a magnetic field, the charges get separated. And the separation of charges produces essentially kind of like a very giant battery. And this giant battery in the core essentially is what helps to kind of give some additional energy to Io, and this can cause these free electrons and everything to, since they're accumulating and creating this kind of battery, a large potential difference, and that creates a lot of power because you're going to have a current flowing as these charges keep trying to move around. And so, again, it's not the main source of Io's power, but it's kind of just an interesting thing to note that, hey, the fact that it's going through Jupiter's magnetic field and has a very strong, very large iron core, at close range, it's going to generate a bit of energy by itself. these two things combined, again, the main thing being the changing tidal forces results in volcanoes. So there you can see a before and after image of a new volcano erupting right off to the side of one. So there's another one. Now, the main effect, another way of thinking of this would be considering a balloon, a blown up balloon that is, around a Jupiter-like planet in an elliptical orbit. So when you get closer to the planet, you squish the balloon somewhat, and when you're farther away from the planet, you don't squish the balloon so much. So this is kind of a model to what's going on with Io as Io is orbiting around Jupiter through those changing tidal forces. Now, balloons themselves don't really heat up a whole lot when you do this, but when you are talking about an entire moon that should be a rigid body, it is going to heat up. And this is something that people actually considered back in the 1970s. In fact, one of the main theorists of this was an astronomer named Carl Sagan, who you've probably heard of, made very popular through his original Cosmos series on television episodes about astronomy. So this was a prediction in the 1970s, and then it was confirmed when the Voyager spacecraft flew by and took pictures as it was going by Io and beamed them back to Earth. So we had a very nice theory there, leading to a hypothesis, which led to an observation that confirmed at least the prediction of the theory. So the result being volcanoes. That large plume that I showed over here, that's an eruption about the size of Arizona. So quite remarkable. Now, another big question. Why are there reds and yellows and grays and greens and whites? Why are there all these different colors? This all has to do with different phases of the element sulfur. Now, I'm not talking about phases of matter like solid, liquid, gas, plasma, etc., etc. I'm talking about the fact that when the sulfur comes out of the volcanoes, along with all kinds of other things like silicates, etc., the S2 gas eventually becomes S3 and S4 after it combines with other S2 molecules. S3 and S4 give you red colors. But after a while, after they've been sitting around for a while, they end up creating S6 and S8, which are kind of the yellowish sulfur color that you're so used to. That's usually S6 and S8 when you're dealing with a sulfur rock that's nice and yellow. The white comes from sulfur dioxide, and dark colors are from other sulfur compounds and silicon compounds, etc. Now, I should mention that sulfur dioxide, you have probably ingested white sulfur dioxide before. It's quite safe. I mean, you don't want to eat a whole cake of it or anything like that. But if you've ever had candied fruit and there's this kind of whitish powder on it, that's sulfur dioxide that's used to preserve the color of the fruit. So here's a depiction of this. You end up having the eruption, giving you red S2 and S3, and then after a while combines to create yellow S6 and S8. And there is another view of one of these volcanoes erupting. So some more views of that. Very nice. And I think this might be that Loki Patera that is that really energetic volcanic caldera. Or the Loki caldera, I should say. So, other views? Take it back, I was wrong. It was Suppan Patera. So, there we go. Now, Io, as we mentioned back when we talked about Jupiter's rings and aurorae, contributes to some of Jupiter's aurorae. So some of that volcanic material gets ejected so high that it becomes part of a thin atmosphere, and that atmosphere gets caught up in Jupiter's magnetic field, creating a plasma ring. So the volcanoes are what end up ejecting the particle stuff, which gets trapped in Jupiter's magnetic field, which then gets corralled into the polar areas, creating a nice auroral display. So, in fact, I should mention, Io actually loses 1 ton of material per second in this fashion. So here's a nice picture of that aurora. This is an ultraviolet picture taken by the Hubble Space. I forget whether it's actually, take it back, I forget if this was taken by Hubble or whether it was taken by the Juno orbiter, but it was overlaid onto a picture of Jupiter taken in visible light, showing the effects of the aurora. And just giving a summary, oh, real quick before I forget, I think this mark right here is directly due to Io. But quick summary of Io. So remember that Io is the most volcanically active body in the solar system. It's so active that it has no impact craters at all. The surface is getting completely resurfaced constantly. The source of heat, at least the main source of heat, comes from changing tidal forces from Io's interaction with Jupiter. So if Io had a perfectly circular orbit, that wouldn't be the case. And the tidal forces would always be the same, and Io wouldn't heat up, and it would just be a dead moon. But because of the fact that it's involved in these gravitational resonances with Europa and Ganymede, it does have these changing tidal forces. And also, since that means that it's at slightly differing distances from Jupiter depending on where it is in its orbit, these changing tidal forces therefore create constant friction in the interior. Now, this whole mechanism that we talked about with Io is also present on another of Jupiter's moons. That's Jupiter's moon Europa. However, with Europa, it is more complicated. It's also present to a smaller extent, which is why the eruptions on Europa are not of sulfur and silicates, but of water, but also why Europa is potentially a very good place to look if you're searching for life in our solar system outside of Earth. So we'll have more to say on Europa next time. I hope to see you then.